Up next, we have Bertrand Mennesson, who's going to tell us, I think, about HWO. Is it Exozodi? Yes, Exozodi's survey of HWO targets with the Roman Coronagraph.
Thank you. So yeah, still on Roman, and thank you, Jason, for this comprehensive talk and introducing the topic of doing science, actually, with a tech demo. I think you mentioned quite a bit the planetary case, both reflected light planets and self-luminous planets. But we should be able to also conduct a possible Exozodi survey of HWO targets, in particular with the Roman Coronagraph. It might be a little less challenging, actually, than planets, and a more guaranteed outcome of the coronagraph, I would say. So it's interesting to look at what we can do with Roman on this front. So I'm going to talk to you about this. Thank you for having me. So I like to start with a little bit with what do we mean by exozodiacal light. I think it's the equivalent of what we have on the solar system and that we define as solar zodiacal light. It was first observed in details by the Kobe satellite. Actually, they needed to get rid of it, and it's a foreground measurement that prevents you from making the actual measurements of the cosmic wave background. But they did fit the observations with a well-known profile. The dust is majorly formed of very small dust particles, which you can see when you look at the zodiacal cloud emissivity versus wavelengths. It drops around 100 microns, which shows that most of the particles are smaller than 100 microns divided by 2 pi. The temperature density profile was also measured. It's around 286 Kelvin in the Earth orbit. It's got an optical depth way below 1, which is 10⁻⁷. And so it's actually a very tenuous dust. It's only equivalent to an asteroid of about 10 miles that would have completely broken down. So it's about 10⁻⁹ Earth masses. But it has a huge flux. So if you were to look at an equivalent of solar Zodi around another system, namely an Exozodi absolutely analog to our own, you would be dominated first by this flux. This flux, turns out, it's about, when you integrate it spatially, it's about 100 times the flux of an Earth or more. And so this is really the distribution that is being measured and observed by and fitted by this so-called CalSAL model of the Kobe observations from the 1990s. And that's what we really define as an Exozodi level of 1 Zodi. So you hear me say 1 Zodi, 10 Zodi, 30 Zodi. The unit 1 Zodi here is to define what we have in the solar system, and we always compare to that. And so it turns out it's about 22 magnitude per arc second square at the Earth equivalent insolation distance around any star that you're looking at. So 1 AU around a Sun-like star, a bit more around an A star. So what do we know today about Exozodi? In fact, in spite of a lot of efforts by NASA over the last 20 years, our knowledge is kind of modest, and it's only based on observations in the thermal infrared, so around 11 microns with LBTI and between 8 and 13 microns initially with Keck. Was part of that with a lot of people. The best results so far have been obtained by LBTI and between 2016 and 2020. The individual quantities per star is huge. It's still 50 Zodis. Remember, it's in the mid-infrared, not at visible wavelengths. The median level that we derive is about 3 Zodis, but it still has a large uncertainty attached to it. So that's what we know today. This is pretty encouraging for HWO, but not final. The problem for HWO is illustrated here. We've been knowing it for quite some time, whether you're looking for exo-Earth in the mid-infrared or in the visible. And you can see this plot here from Aki Roberge and collaborators from 2012. If you are on this line here, even for an 8-meter telescope, as soon as the Zodi is about 5 times solar, it's much brighter than the exo-Earth. It's like 5 times brighter, and so you can imagine that at 20 times the solar Zodi level, you're completely dominated by exozodi emission. So we'd like to know about this. Some more details about Exozodi, which actually increases versus wavelengths. I don't have the time to really go into the details here, but the situation gets worse when you go from 0.5 micron to say 1.5 microns, simply because the diffraction limit scales with wavelengths, and so your photometric aperture gets larger and larger with the wavelengths, so you collect more and more of that dust emission as you go to longer wavelengths. So the limitations are well known. The mid-infrared measurements that we have so far are kind of spatially integrated over a few hundred milliarc seconds. We don't really know the structure. We have very weak spatial information. A solar Exozodi-like model is assumed to convert these measurements in the mid-infrared to what we expect at visible wavelengths. That's a huge assumption in order to extrapolate these results. Even more, that there is evidence from joint mid-infrared and infrared interferometric observations that some stars, not surprisingly, have very different dust distribution than the sun around them. For instance, tens of thousands of Zodis very close to the star have been observed in a few cases. And the last assumption here is that we've been treating so far all of these yield simulations, or the number of planets we could detect with HWO, assuming that Exozodi signals are only adding photon noise, so they can be removed first completely with in-shotoi noise, and then you're left with just noise but no bias, which is also another strong assumption. And you can see it illustrated here on the right, where in the case of a 4-meter telescope, we did vary the Zodi level from 1 to 20. In the 1 Zodi case, you're able to retrieve the position of your planet. In the 20 Zodi case, you're actually retrieving a dust clump, which is a resonant dust clump with this planet. So we'd like to avoid that situation. Luckily, there is a coronagraph with Roman, which we've been really saying for a long time should be able to answer a lot of quantitatively that question of how bright the Exozodi is at visible wavelengths. We believe that we can access about 70 of the HWO targets with CGI, and we should be able to do a survey of all of these targets in about a month, and maybe tens of them in a week, down to 100 Zodi level or better, depending on the exact performance demonstrated. But this is really a science case that's kind of resilient to the level of contrast you achieve. Even 10⁻⁸, even a few 10⁻⁸ should be enough to yield new data. So another feature, if you will, of the coronagraph, which Jason mentioned before, is that we have a very extended PSF. So if you look at the encircled energy versus wavelengths for PSF, that would be in the middle of the dark hole at 6 lambda over d or something. It goes up like you would expect. So there's a bright core at the center, which you see here, a sharp increase. But then it takes a very long time to saturate. And that's because about half of the energy is being diffracted very far from the peak. And so that's a bit of an issue for really planet observations, because you throw a lot of the light out. For disks, what it means is that you're actually going to be detecting in your XCAM camera a lot of light which is coming from other parts of the disk. So it's a bit of more of a zero-sum game, because the source is extended, so this is diffracted away. So it makes things a little bit brighter than you would expect from a point source. It also makes them it makes it a little bit more difficult to assess where the dust is coming from in the image. So again, I'm not going to go into the details here, but if you were to, for instance, assume a Zodi distribution of dust like this, so this is the flux as a function of separation on the sky, what you're going to see with CGI is something like this in this case, which is much higher than you would expect from a point source. And so, you cannot take this as first value. It has very small resemblance to what you actually were injecting. We are not seeing very close to the star, because we are remember it canceling starlight and everything that is very close to the star. So that results in some kind of a pile-up of dust, apparently very close to the inner working angle in that extended case. So what we have to do is some forward modeling of this effect, and we were wondering whether we are able to retrieve the actual distribution in some simple cases. So what we are after really is the surface brightness, again, at the Earth equivalent insolation distance, SB of EID, The inclination, the PA, the basic geometrical properties of the disk is inside radius, is outer radius, and maybe the power law of how it evolves versus separation. So we generated a number of very simple fake models, and then we run an MCMC, that's work by Jorge Lopzeison at JPL, together with me, to do some very simple retrievals of these parameters. We have worked with noiseless images as a first case scenario just to see if that works at all. It does work at all. I don't have the time to go through all the details, but actually we are able to retrieve all physical parameters with high accuracy, even the inner radius. It turns out that this dust, which is coming from inside the mask, the diffraction helps you there because you would not be able to see it because it's below the mask, except for the diffraction that is actually throwing some of that light where you can see it in the dark hole. So this is actually good news. So what we propose is for the first 6 months of the mission to conduct a pilot survey of Exozodi around some variety of stars. That the idea is to motivate a possible broader survey later on during the mission, or possibly through an extended mission. And so we're going to start with 7 targets, which have been all chosen from the list of white paper call that Jason mentioned before. So there's a variety of solar-type stars, A-type stars, some with, some without previous Exozodi detection. So you can validate your results, but also do a little bit of a search, and really try to assess how well you're doing in practice. Thank you. So as a summary, so Exozodi at a few solar level will dominate over exo-Earth flux per resolution element at visible to near-infrared wavelengths. We already know that. It's been measured in the mid-infrared at a typical level of 3 Zodis, but with a very large uncertainty. But it's never been measured around sun-like stars at visible wavelengths, not at the 1000 solar Zodi level, which is much bigger than what we care about. The Roman Coronagraph is designed to detect and resolve these structures for the first time at optical wavelengths at much better level, 10 to 100, depending on performance demonstrated. And it is supported by initial, there's more to do, but by initial MCMC forward modeling retrievals. So a pilot survey will be conducted during the observing phase. I think it has 3 different campaigns over the first 6 months, include 7 stars. And I think I will stop there, and thank you very much.
Thank you, Bertrand. Any questions for Bertrand? Happy to kick us off with a chair question first. Okay. Can you comment on, so essentially you don't exactly know the Zodi level for these, and you're saying there's implications for HWO. What are the implications?
So we know the level of some of them, which have been detected by LBTI at the several hundred Zodi level. So those, if they are really at the 100 Zodi levels in the visible, once again, it's been measured in the mid-infrared. We don't know what they are in the visible. We have kind of physical arguments that said it should be about this breeze brightness also at visible wavelengths. But if, for instance, the Exozodi level is at 100 Zodis around a star, it's impossible to see exo-Earth in that particular system. So given the price tag of any stellar observation with HWO, we'd like to know that beforehand. Yeah. And so know which stars have a lot of Zodis, and also design the HWO telescope accordingly, because if a lot of these stars have very high Zodi levels, it calls for a bigger aperture or some other means for data reduction.
So basically you may remove it from the target list for HWO entirely if it's just too, the Exozodi is too high.
At least for exo-Earth, it would be okay for outer planets, but it would not make it to the short list for exo-Earth observations.
Okay. Any other questions in the audience? I think people are tired. I think, do we have any questions online? No. All right. Last call. Okay, let's thank Bertrand again. Thank you. Thank you.